Alrighty, let's get this going. Okay, and creatures already at it. It's always fun. Today we're going to talk about reaction yields. So we're going to finish off our discussion of Chapter 10 stuff with creature in the background. Creature shush. Alrighty, so far we have seen how alrighty, hold on, let me go get him. Alright, here we have a creature. Oh my goodness. Okay, you can stay on my lap, buddy, okay? We've seen how to calculate the theoretical yield of a reaction. Remember that was just kind of the maximum amount. And of course now Oz goes. Oz shush. And so the theoretical yield was the maximum amount of product that we could make. And so it's called theoretical yield because in reality, the actual yield is always lower than the theoretical yield. And this can be for any number of reasons, one of which could be that side reactions happen. Or we have kind of solubility issues. You don't need to memorize these or anything, but these are just kind of reasons that we never get the full yield that we would expect. There's just kind of some product. You kind of just leave it behind in your glassware. Like it's hard to scrape every last bit of it out, so you do lose a little bit there. You just kind of have just some reactant doesn't react for any number of reasons. Maybe got trapped inside a particle or something. I mean, there's all sorts of reasons that we don't actually get the full yield of what we're looking for. And so in order to kind of describe this phenomenon, we have something that's called the percent yield of a reaction, where it's going to be the actual yield over the theoretical yield times 100%. So notice we can calculate this using our stoichiometry. That's our kind of unit conversion that we've been spending the last couple of days doing. But the actual yield can't be calculated. Or let me let's see. You would be either given this or given the percent yield. So the actual yield is not something you're going to be able to just calculate directly from a reaction. It's something that if I give you the percent yield, you can find the actual yield. Or if I give you the actual yield, you can find the percent yield. So we know that we can calculate the theoretical yield. So let's do just a quick example of that. let's say we had our, I think yesterday we had a reaction with ammonia that we ended up producing 3.33 moles as our theoretical yield. Remember, we did that one where we took the we had the nitrogen and the hydrogen, we put them together, and we made our 3.33 moles of ammonia. And I think for that one, the hydrogen was the limiting reactant, and it's all stuff from yesterday. And let's say we only got 2.89 moles in reality. The percent yield we have a little formula here. So that's the actual yield over the theoretical times 100%. These just need to be the same units. Doesn't matter what unit you're looking at. If you're looking at atmospheres, if you're looking at moles, if you're looking at grams, if you're looking at liters, whatever it happens to be, you can use whatever unit you like as long as they're the same unit. So in this case, we have moles for both. So we can say that it is going to be our actual yield. So that's what we got in reality, our actual yield. Oh, shush. He's just like kind of grumbling down there. It's pretty funny. What are you upset about, mister? So notice moles cancels out, of course. And so doing this, bust out our calculators here. 2.89 divided by 3.33. We get 86.8%. And so this percent yield might be something that you might read as the reaction is 86.8% efficient. That's one way of talking about it. So we've lost about 13% of our reactants. Either they're not reacting or they formed a different product, or who knows what. Maybe we lost some because we accidentally opened the reaction vessel and some of it escaped. So, I mean, there's all sorts of reasons. Human interference, another one. So that's kind of all that it is. So you just take your theoretical yield, which you calculated from stoichiometry. You take your actual yield, which is either given to you. If you're calculating percent yield, the actual yield will be given to you. Or I could say, okay, a reaction is 72.1% efficient if the theoretical yield is 82.6 grams of product, how much can be expected? We can do something like this as well. So we don't know our actual yield, right? But we can solve for it. It's just an equation. If we do this, we get 0.721 times 82.6. We get 59.6 grams. So that's what we would be able to expect out. All right, or we could say same reaction. but I want to get 100 grams. How much should I prepare to make? So hopefully, I mean, this is a little bit of reading here, but I want this amount. So I'm making this product. I want to get 100 grams. However, I know that this reaction is only 72.1% efficient. And so I can kind of plan ahead and be like, okay, well, if I know I'm going to lose the creature, I'm going to lose some of mine to side stuff or whatever, then I can take that into account when I'm planning out how much to make. And so this time we're kind of figuring out what the theoretical yield should be. I want to plan that theoretical yield. So same reaction. We know we want to get out 100 grams. We don't know what our theoretical yield will be, or what we should plan for it to be, but we can solve for it. If we do so, 100 divided by 0.721, 138.7 grams. Alright, creature, here you go. Oh. He's heavier than some of the others, so hard to just hold him. So I should plan. I should aim to make so that I end up with 100 grams. All right, so you can kind of plan ahead. So again, you can kind of think of this as, like your cookie recipe. You've made your cookie dough. The recipe says it's going to make 24 cookies. But, maybe you accidentally made one of the cookies a little too big, and so now you only end up with 23. And so you have lost a little bit of your yield. Or say you ate half of the cookie dough while you were rolling out the cookies. You just lost half of your yield. So, all sorts of reasons happen that your yield would be less, but it always is less, right? And so, for, any number of reasons. So, if you, really want to make 24 cookies, maybe you should plan to make 36, just in case. So, it's always good to have a little bit of extra so you can kind of plan a little bit ahead there. So, let's up the ante here. Let's take a reaction. How about we do... We'll do a nice one. Okay. I'm really thirsty here. This reaction is 98.2% efficient. If I want how much hydrogen am I going to need in grams? So now that we throw in this kind of reaction yield idea, we can say, okay, well, we know how much hydrogen we would need to make 200 grams theoretically. But if we wanted an actuality, we have to use our equation here. They're always barking at the same dog. My poor little bee one here. He's always getting barked at. So I want 200 grams. I guess I only gave you 3 sig figs for that. So let's go ahead and see what our theoretical yield should be. So our theoretical yield that we were going to aim for theoretical. Now that we have that, that's grams of water, right? Now we can go ahead and do our funneled stoichiometry business that we've been doing all week. We have our water. We're looking for hydrogen. The problem is asking for grams of hydrogen. And we are given our theoretical yield of the grams of water that we're shooting for. We're aiming to make 203.7 so that we end up with 200. Taking into account side reactions or unreacted things that are going to happen. Typically, reactions are given as the highest yield that they'll make. This is kind of something that we do in science. Is we do a reaction, we report the yield. Other people do a reaction, report the yield, and we kind of see, roughly where it is. And so if you repeat the exact conditions, you should presumably end up at the same yield percentage. All right, so grams to moles, that's something we're going to use molar mass for. Of course, we have our reaction coefficients. And we have another moles to grams, so that's molar mass again. So we can go ahead and take this water here. Water's molar mass 18.02 grams. We have our reaction coefficients. And then our last molar mass is going to be, 2.016? And these are for hydrogen. So, let's do the math. So notice on my calculator, by the way, I still have all those crazy numbers from before. I'm not going to round it. So remember, try not to round until the very end. Just to make sure. If you do this, you get 22.8 with the appropriate sig figs. So I've written 203.7 just kind of as is, but I don't actually clear my calculator. I'm going to keep going. So we're going to need 22.8 grams of hydrogen to get that amount of water out. So that's how much we should put in to theoretically get 203.7, but in reality we're only going to end up with 200 because there are some side reactions or whatever that's going to take away from our yield. So it's really just kind of the last little bit here. Let's do another one, perhaps. Let's say what reaction shall we do today? Yes, let's do this one from before. Alrighty. I add 5 grams of copper to 50 ml of 0.30 molar. I guess I'll give it one more sig figs. Part A. How is there still food there for you to eat? You guys have been fighting over it all morning. Weird. Okay, so with this, we have enough information about 2 reactants, right? We have something about copper. We have something about silver nitrate. Oh, I guess I need to tell you what you're solving for. Theoretical yield of silver. And let's say in grams. Alrighty. So, limiting reactant problem, we have multiple reactants that we're going to need to calculate. So, we have one for copper. So we're going to go from moles of copper to moles of silver. Our problem is asking for grams of silver. So hopefully this, setup from kind of the middle to the end should be the easy part for you guys. The middle is always the same. It's always moles to moles. And then you just go from the moles of whatever you're looking for to whatever unit you're asked for. So in this case, grams. If we're looking beforehand, though, that's when things get a little tricky. We have to go back to our problem and look. It looks like we do have grams of copper to start, and we know we can go from grams to moles. That's going to be the molar mass. This is going to be our reaction coefficients, and the molar mass again. So if we do this, 5 grams. Ooh, let's see. Let me get a periodic table. Is there one up here? Yes. Alrighty, copper, where are you? Copper, 63.55. Forgot a coefficient there. We have our mole ratio. And then we have silver's atomic mass, which is 107.9. Alrighty, so we can go ahead and do this. So 5 divided by 63.55 times 2 times 107.9. And now Miss Jersey's out there barking. So let's say 16.98 with 3 sig figs. Remember, for theoretically, we need to do for every reactant that we have. So our other reactant is silver nitrate, so we're going to need to do a unit plan for that. It looks like this time we're given milliliters and molarity. So we know that with the molarity we can go from liters. And since we're given milliliters, we'll start with that. As always, we have our reaction coefficients in the middle. We have a molar mass this time on the right side. We have a molarity this time for our solution. And then we just have our metric conversion to start. Let me just look up silver nitrate's atomic mass. Okay. So it looks like we're starting with 50 mLs. Our molarity was given to us as 0.30. That's moles per liter. We have our 2 moles of silver nitrate for 2 moles silver. And then we have that atomic mass from before. Doing this math. Oh, we don't need the molar mass of silver nitrate. Why did I even look that up? See, I told you don't need molar mass most of the time. Times 0.3 times 107.9. We get 1.6 1.619, which we will round to 1.62. This is going to be our theoretical yield. Remember, the smallest one will be our theoretical yield. So all that work to just get one number. So let's say I only get 1.25 grams. We can figure out what the percent yield is going to be. So this is going to be an actual yield here. And so if we remember, the percent will be that actual yield over our theoretical yield. It's a percent. So let's take our 1.25 divided by whatever we just calculated. And you get 77.23%, or it looks like with 3 sig figs, 77.2%. And so that would be our reaction percent yield that we'll get from this reaction. All right. Any questions on any of this stuff so far? It's really just adding one more kind of little bit here to the end. Yes, that's all it is. Yeah, it's just proper planning will get you where you need to go. And so that's why you have plenty of homework on this. Very exciting stuff. And so that'll be due Saturday, don't forget. So I would definitely take the time to have a look at that. Once you, if you can plan it out properly, this should really be no different than any of the other dimensional analysis we've done. The only thing we're throwing in here is the reaction coefficient. That's the only new thing. So hopefully just doing it day after day after day will hammer it into your brains. But we'll see. So, cool. Alrighty. Why don't we do... Let's just do one more. Alright, let's see here. Decomposition reaction this time. We'll put a little bit of heat into it. All right. Hi, Miss Jersey. Okay, let's say we have 50 grams of calcium carbonate is heated. And we'll say 85% of it reacts. How many liters of CO2 are produced at 1 atmosphere? And let's see, when we're heating this, how much should we do? How about 500 Kelvin? So we have here our starting material, our reactant information. We have here a percent yield that we're given. and we're asked for the liters of carbon dioxide that are going to come out. We've given some other gas quantities there. With this, if we wanted, another thing you can do with percent yields, you can just mess with your starting amounts as well. If we know 85% of it is going to react, we could just start with that number and just carry through to the end if we wanted to do it that way instead. Or we could solve it using 50 grams and then multiply by the 0.85 at the end. Either way, it'll all work out. But since we're trying it new this time, let's see. So that means let's see. I guess I have a 0 there. 50 times 0.85. So we know that only 42.5 grams will react. So we can just go ahead and start with that 42.5 and just go straight to the end and not have to worry about it anymore. So either way, or you can take the 50 and go and then multiply by the 85% at the end. Again, multiplication works no matter what order you do it in. So, but for this one, let's start with that 42. So, planning time. We got moles of calcium carbonate to moles of CO2. We're asked for liters of CO2, not O2. I guess we'll continue the plan. And we're given grams to start. CaCO3. There we go. As always, reaction coefficients in the middle. Going from moles to liters of a gas, we're going to use volume equals nRT over P. Ideal gas, I'll just solve for V there. And then we have our molar mass. Alrighty. Here we go. So, 42.5 grams calcium carbonate. I think we did have calcium carbonate's molar mass. It was like 100, right? Yeah, 100.09. Oops. Our reaction coefficients are both 1. And so note that we still write it every single time, even if they're both 1, because it's always good to just kind of be habitual about it, do the same thing over and over. It'll get drilled in your brains. But also, if we want it to be like correct unit conversion, we still need to make sure that everything cancels out. So we will always include the 1 over 1 if that's what it is. So just good practice. Alrighty, and so if we're going to look here, we're going to need to multiply by these 3 here for our next conversion. Now that we have moles of CaCO3, we're going to multiply by our R. And then T was what, 500? Yeah. And then the pressure was 1 atmosphere. Doing all this fun stuff. Let's see what we get. 42.5 divided by 100.09 times 0.08206 times 500. Do this, we get 17.4 liters of CO2. And we're done. That is our actual yield of CO2. Or that we're the theoretical actual yield. So assuming it is 85% efficient, that's what we are going to get out if we heat up our 50 grams of calcium carbonate, releasing the CO2. So that'll be an actual yield that we got out there. All right, because we had messed with we had already taken into account the reaction yield at the start. All right, so you could do it at the start or at the end. Doesn't matter. Whichever way you like, it'll work. All right. Any questions on that one? And yes, again, it's just lots of planning. If you can do the proper plan, then it's just a matter of, once you set it up properly, then it's just a matter of plug and chug and off you go. Let me just take a look at our homework here. Let me get to one of your classes. Oh, I have so much to grade still. Okay. Reactions in stoichiometry, where are you? So it's got stuff on both reactions and stoichiometry, right? So we have 12 problems here to deal with. Some of them are just on reactions. Some of them include stoichiometry stuff. You should check. It's always a good idea to check. For these ones, I've just been kind of giving them to you already. If you look on number 8 on the homework, by the way, that one is not balanced, for example. So it's always a good idea to check. Oh, I guess we haven't talked about number 8 yet, so we should probably do that. Alrighty. By the way, we can use this percent yield stuff to figure out how much extra reactant you have also. If we take a look at that, what did we have here? If we take a look at this stuff with the silver nitrate, let me just copy the numbers here. So we had 5 grams of copper, gave us 16.98. And then the other one we got 1.62. We can also figure out so we know that silver nitrate was our limiting reactant, which means that we're going to have extra copper around. And so what you can do as a result of this, you say, okay, well, how much could I make from the copper versus how much do I actually make from the silver nitrate? It's a similar thing here. We can see that if we actually make 1.62 grams over what we should have been able to make, if we take that ratio combined with what we started, if we just take a look at that real quick, 16.98 times 5, we see that we actually only used up 0.47 grams of our copper. And so if we want to see the amount left over, that's going to be our initial amount minus the amount we used up, which will be 4.52. So this is kind of the initial amount. This is our amount that we used. This was the amount that the limiting reactant makes. And that's how much we could have made with our excess reactants. So it's just seeing how much of it we actually used. So if you see we used roughly about 10%, right? Like 16 over 16, or 1.6 over 16 is 10%. So we used a little bit under 10% of our copper that we started with. So we have a little bit left, more than 90% of it left over at the end. So that's another thing you can kind of do with this percent yield stuff. And this is going to be the the copper we started with. So that's another thing you can do with this. So just, there will be a problem on that on your homework, so just keep that in mind. All right. The last thing that we're going to throw here is energetics. So we can also use energy of a reaction. So if we have some glucose being burned, or otherwise used up, oftentimes for reactions, as you will come to dread next semester if you continue on taking 111, you can have delta H's for reactions too. So we saw that we had them for phase changes, so like solids going to liquids, we had the delta H fusion. We can have delta H's for reactions as well, and they tell us how the energy changes over the course of a reaction. For this particular reaction, we're looking at an energy change of negative 2 million joules, essentially. And what this can be used for is this gives us some more reaction conversion factors using our reaction coefficients. So this tells us that 1 mole of glucose equals that many kilojoules, our delta H. We also get that 6 moles of oxygen equals our delta H. We get 6 mole of carbon dioxide equals our delta H. Notice these are again just the coefficients. And the last one, we get 6 moles of water equals our delta H. So your reaction coefficients can be used to figure out the energy of a reaction too. So we could use these in addition. So if we see here, if we burn 100 grams of glucose, we can do this too. So when we're planning this though, instead of going from moles of one thing to moles of another thing, we just go from moles to energy. We can just do that. That's what delta H is used for in reactions. You go from, instead of going from moles to moles, you will go to moles to energy. So you can do that as well. And it looks like in this case we're starting with grams of glucose. So we have two conversions here, so therefore we need two conversion factors. If we're going between moles and energy, that's what delta H is. And then we also have our reaction coefficients there. Wow. Coefficients. I'll say and, not plus, just to put that there. And then this one we have the molar mass. So here we go. 100 grams. Molar mass of glucose is 180.2. Our reaction coefficient here is 1. And so we can do this. 100 divided by 180.2 times 2802. So we're looking at 4 sig figs. So we're looking at a total energy change of negative 1,554 kilojoules. Or we could, so just remember negative just means it's exothermic, right? So that's the amount of heat that would be changed there. So we can just leave it like this, or if you really wanted, we could say it's the positive number is released. Let's just leave it as is. That'll be the best thing there. So for right now, we can just ignore the negative sign. It just indicates that heat is released. So we could say this reaction produces of that much energy as we go through it. All right, or we could say if we produce 100 grams of CO2, how much energy was released? We could do that too. We can just use any of these parts of this reaction wherever it went. Oh my gosh, there it is. So delta H will just be your conversion factor between energy and moles. Obviously, you'll be given the delta H, or you can calculate it by saying, okay, we've produced this much. It's just like anything else, you know, it's kind of a formula type thing, right? I can give you enough information to solve for one little bit. So we can go from moles of carbon dioxide to kilojoules. And we're given grams to start, so we can do this. We have delta H there, molar mass here. If we zip through this, 100 grams. Carbon dioxide's molar mass is 44.01. Don't forget your reaction coefficients. Our reaction coefficient here is 6 for the reaction we're given. Okay, let's do the calculation. And we end up with negative 1061 kilojoules. And so we can say that much is released as we go through it. All right, let's just do one more here. Let's say that we have okay. We can just go from energy to other stuff now too. Alrighty. We know we're going to end up with moles of oxygen at some point here. We are asked for liters of oxygen, which is going to be our gas law. We can go from kilojoules to moles by using delta H. I guess that will be consistent with my color. Or we can say, we can use our STP shortcut here as well. We could just use that as our conversion factor. It's a little faster to do it that way. So let's just go ahead and do it. So, again, if you want to just forget about the negative signs, go right ahead. Don't even worry about them. Just make your answer positive and throw the word released or whatever. That's fine. Just copy the word from the question. So this one says we're producing it. So don't worry about the sign again. All right. So if we're going from kilojoules to moles, we have to use our delta H. For this reaction, it was negative 2,802 for 6 moles of oxygen, our reaction coefficient there. Of course, every reaction has a different delta H, so this one just happens to be for this particular reaction, for glycolysis here. Remember, at STP, we can just use 22.4 liters. We don't have to actually do the PV equals nRT, but you can. You'll get the same answer, so just a little bit time saving to do it this way. Okay, so let's start. So 1500 times 6 divided by 2802 times 22.4. And so we're going to end up taking up 70. Let's see, we have... Here, we'll make this have our sig figs there. So 71.95. And so you would expect to use just about 72 liters of oxygen to get about this amount of energy by burning glucose. So you can do all sorts of crazy fun things with this. All right, so let me very quickly copy our... Oh, don't. Okay. Let me copy our thing from yesterday, just to kind of summarize this bit. Yes. Okay, we copy the chart. Okay, let's bring this into today's notes. You don't need the exam key for 111 or 113. Okay. Oh my gosh, I have to type this. Okay, all the way down. Okay. All right, so the only thing we've thrown out here one more little bit, and how we do that is delta H. So we can go from either of those moles to delta H, or rather to kilojoules using delta H. So it's just one more little bit here that we're throwing out. right? So obviously we're dealing with matter for most of this chart, but we do have a little bit of energy here that we're going to associate. So we can do that too. All right. So we're done with chapter 10. Hooray. Tough chapter. Lots and lots and lots of math. As you can see, you do have 12 problems. Don't underestimate them. They're not that short. So I would make sure you have enough time to do them. Don't forget it's due Saturday so that you can look at the key on Sunday. Make sure that you're doing it all correctly. And then Monday is going to be your exam. So your exam is just on chapters 9 and 10. That's reactions and stoichiometry. Tomorrow, well, let's see, actually. Tomorrow, we can either... tomorrow, let's just take the day off, I think. Thursday, we'll have our review session for... or we can do it tomorrow. Doesn't matter. Let's just do it Thursday. We'll give it a little bit of time to sink in. So Thursday, we'll do our review session. So we won't have a stream tomorrow. Monday will be your exam, the 26th. Then we'll spend the other 2 days starting chapter 11. We'll finish chapter 11 the following week, the week of the 3rd. And then we'll spend the rest of the week reviewing. And then we will have our final exam on the week after that. So let me just write this down. As of course it's all the way at the top still. So let this sink in tomorrow. Remember, you guys got to give me questions if you want to do a review. So, homework questions, old homework stuff. Can we do this type of problem again? Can we see 2 more examples of limiting reactant? Whatever it is, post stuff for me to do. We'll do that. So exam 4 will be on the 26th. And then it's going to be chapters 9 and 10. We're going to do chapter 11 there, and then probably maybe 5, 3, and 4. We're going to finish off chapter 11. And then probably 5, 5, we will relax again. 5, 6, we'll have our final exam review. And then what I plan to do is I'll give you guys 2 days to do your final exam. So just to make sure that you can fit it in your schedule there. So you'll have both Monday and Tuesday to work on it. It'll be multiple choice, just like always, for your final exam. So we'll have that there. Okay, so that'll be our plan for the rest of the semester. So if there's anything else, I will see you Thursday. So post questions if you'd like me to go over anything again. As always, you can just post written questions in Discord. I have no problem with that. So, all right, that's kind of our schedule for the end there. So, awesome. Alrighty, I'll see you guys on Thursday then. Take care.